us on the Blue Swan. Today we have Tal David and Amit Ben Kish, who are the founders of Quantum Art, which is a quantum computing startup that raised an $140 million Series A, the largest Series A financing in quantum computing, and was subsequently prematurely featured on the New York Stock Exchange, which is foreshadowing if I've ever seen it. And so, on that note, would you guys mind sort of discussing yourselves, your work, and anything you'd like to say?
Hi, Sean. Thanks for having us. So my name is Tal David. I'm the CEO and co-founder at Quantum Art, a quantum physicist with experience in academia, industry, and government. I was head of Israel's national quantum strategy.
Thank you for having us. My name is Amit Ben Kish. I'm also a physicist. I did my postdoc at Boulder with the Linenool. As you probably know, won the Nobel Prize for quantum computing based on trapped ions, and I'm the CTO.
I'd like to just jump straight to quantum AI. And so, you guys have successfully formed partnerships with a number of large companies, some of which include NVIDIA. And so the nature of what quantum spins do creates a completely different set of possibilities computationally when it comes down to either the discrete or probabilistic side of AI algorithms. I'm wondering if you would be willing to touch on how that changes the nature of AI computation and then also how it will evolve with it.
AI is a real revolution. It's disruptive. But basically, it's a software revolution. It's based on the same CPUs and GPUs that we're running the AI applications on. Quantum is a whole different story. It's a paradigm shift. It's a new kind of logic, and it comes from the hardware first. So essentially, AI and quantum will complement each other, and anything that you can do on AI, you can implement now not on the CPU and GPU, but rather on the QPU, the quantum processing unit that is at the heart of quantum computers. Quantum will accelerate some of the workloads that AI is doing, okay? It could be optimization problems or learning problems or protein folding problems and so on. And the speedups that are expected when quantum will accelerate AI could be a factor of 1,000,000 or more in some of these workloads. That's one. The other thing is that at the same time, the energy consumption of quantum computers is drastically less than what you find in AI data centers. And there are predictions that within the next 3, 4, 5 years, the difference between working in AI data centers as we know them today and how much power they consume and working in a hybrid quantum and classical AI data center would be orders of magnitude. The energy consumption benefits would be on the scale of the energy consumption of whole countries in just a few years' time. So that's a very, very big deal, especially when you think about AI data centers today starting to build nuclear power plants in order to supply the energy for them. So that's a real disruption. And then the third part is that AI is also helping quantum in the other way. We're using AI to design our quantum computers, to carry out very complex problems in quantum and so on. So it's a kind of a two-way street.
So we're working with trapped ions and we're working with multi-qubit gates. And as quantum computing is a universal set, in practice, you can do anything, including AI. So any type of computation you would be able to do on a classical computer, you can do on a quantum one, except the fact that you have like exponential memory and you can do things much faster with much less energy. There was the field of using AI on a classical computer, and the analog to this is called quantum machine learning. And what we're also doing is trying to figure out algorithms at which quantum will enable getting to results much faster, easier, and sometimes wiser.
There's been a ton of investment in everything from nuclear power to underwater data centers that are essentially being built, towards the bottom of the ocean. The computational cost and sort of the energy consumption related to it is a massive bottleneck. How do you see quantum computing moving more towards storage?
The strength of quantum computing is the ability to calculate large amount of data. It's not the streaming of data, but the amount of the ability to calculate while using a large amount of information. So Actually, the memory is built into the computation process. You start with a very small amount of qubits that enter the system. You get out not so many qubits, but there is an exponential number or volume that you can actually address and can calculate. So you would reach direction that which you would not be able to address before. So for example, if you would like to calculate some chemical reaction, you won't rely necessarily on a large amount of data, but we would let the computer start from an initial state, calculate the process, and give you the result that usually you won't be able to get using classical means because you don't have the ability to either calculate fast enough or have the storage to have all the information, whereas this information is already built into the process or the algorithm itself.
Let's say that you are a pharma company like AstraZeneca or Pfizer or any of these guys, and you want to develop a new drug, and you're looking at molecules having, let's say, only 300 atoms. That's a very small thing, right? In order to simulate that, you need to span a computational space, which is huge because you have 300 atoms. How do they connect with each other? How do they relate to each other? You have many, many possibilities. When you're encoding that into a quantum computer, each quantum bit or qubit, as Amit said, is holding part of that information, and the scaling is exponential, meaning that you can encode the whole computational space in just 300 quantum bits or qubits. And the computational space, or the number of possibilities that you can compute in the quantum computer in parallel, is 2 to the power of 300, a number which is larger than all of the particles in the universe. So the input and output from the quantum computer is just 300 bits. But the computational space that we calculate on is at the size of 2 to the power of 300. Okay, so it's very little in, very little out, but in between, we have extremely high complexity calculations being available using quantum computers. And no classical computer on Earth can even get close to that.
It's more a matter of the computational efficiency than it is the type of particle that the data is essentially being processed through. How do you eventually see the quantum computing branching out further into the hardware space? Because right now it's really limited more towards institutions, and so the focus on drug discovery or algorithmic trading, radar for solving traffic issues, all of that is very, very much done through institutional partnerships. How soon do you see quantum chips being embedded in laptops or even smartphones down the line? And then how do you see some of the temperature issues being solved with that? Because the temperature for which the qubits need to run at is like absolute zero, and that's not the easiest thing to do when dealing with laptops and cell phones.
Yeah, well, I'm not sure we'll see quantum computers in your iPhone anytime soon in the sense of the quantum hardware. What you will see is quantum computers being added to data centers and to cloud providers, and then you can access them through the cloud from your iPhone. And actually, you can already do that today with about 20 different vendors offering quantum computing services over the cloud, what we call quantum as a service. So I would not expect the actual hardware to be miniaturized and go into laptops anytime soon. Where is the time that this will have the ChatGPT moment in the terms of the commercial viability, not so much in terms of consumer use? I would say that there are two important points in time. The farther out point in time is about mid next decade, where companies will get to a level of about 1 million qubits. Okay, right now we are at the level of a few tens or maybe 100 qubits in the systems that we have today from all of the industry partners and companies involved. So mid next decade, we'll get to 1 million qubits, and that is considered the utility scale and unlocking the full potential of quantum. And you could see that target being defined by governments like a big DARPA project in the US, a similar project in the UK now, and so on. So that's one point in time. The other point in time is when are we going onto the playing field, so to speak? When is the initial point where quantum will start to show usefulness? We call that point quantum advantage, okay? And quantum advantage, in order to get to that, you need to be in the order of a few tens or a few hundred logical qubits, which is a measure that can be achieved when you have a few thousand or a few tens of thousands of physical qubits. This, according to all of the roadmaps, including Quantum Art's roadmap, is expected to come at the next 1.5 or 2 years, end of 2027 or maybe early 2028. And that will be the first time that quantum will surpass classical computers, even the most high performance of them, in commercially interesting problems and not the boutique demonstrations that we're starting to see in the last few years. Okay, so these are 2 points in time.
Yeah, maybe I'll just start for a second on the cooling process that you've mentioned. So yeah, that could be a bottleneck, but it depends on the modality. So in some cases, you would like a large dilution fridges. That what these are the pictures you usually see in the media, and I think it's related to superconducting qubits. It's not necessary in all modalities. For example, using atom or ions, you don't need to cool the whole system. The trick is instead of cooling the whole environment, you just cool the qubits themselves or the atoms or the ions of the whole information. So there is orders of magnitude of material size that you would need to cool. In our case, for example, Tom mentioned like thousands or so qubits. We need only to cool them. The trick here is based on Nobel Prizes that people got like 2 decades ago, is using optical power or lasers to cool particles into the ground state or almost to the absolute zero. So the trick is to use lasers, which are very efficient, also to cool the ions. That's one thing. The other thing, using ions in our case, as well as using atoms, the qubits themselves are perfect. You know, God made them perfect. All of them are the same. We apply magnetic field, electric field, lasers, and all of these needs to be very stable in order to make the process happen. This can have some error, which is the error that is related to the physical qubits. In order to surpass this problem as well, what people do is they take a few qubits, say 10, 20, and they bunch them together, and they are used as a logical qubit in order to operate a system without errors. As long as you are fixing errors faster than you're having errors, you can have an infinite circuit depth that will calculate anything that you would need. And there is also a difference between modalities. Whenever your fidelities are very good, this ratio between logical and physical is different. And for trapped ions, the ones that we're using, this is considered very relatively small, and we're talking about 10, 20, 30, depends on the specific code that they're using as a measure for getting logical qubits to be used as part of the process.
Why do we need a few tens of logical qubits or a few or maybe 100 logical qubits to go on the playing field and start to be commercially viable? It is because it is starting to be considered as an agreed upon fact that when you get to that level, it means that you're surpassing whatever high performance computers can ever dream of doing. Okay. If you take an HPC, high performance computer, and you want it to emulate quantum computer, the computational power of the strongest classical computers out there is equivalent to about a quantum computer with 50 perfect qubits. Okay. Noiseless qubits. If I have a quantum computer with 50 perfect qubits and I add just one more, we said exponential, the scaling is exponential, right? So we're now doubling the power related to the strongest high performance computer in the world. If we're adding another qubit, now I have 52, I'm now 4 times as powerful as the quantum computer, as the classical computer can ever be. Okay, so it's really a dramatic thing. Now, what's the caveat here? The problem is that our qubits are not perfect qubits. Okay, they have noise, as Amit said. We're taking a bunch of them and encoding them like an effective qubit that has lower noise, such that the threshold to do correction of mistakes on the fly is beneficial and not harmful. And so once you have a few tens of logical qubits, let's say up to 100 logical qubits, it means this is the point where we're surpassing the most powerful quantum classical computers out there in the world. And this is considered to be the beginning of commercial viability, or what we call quantum advantage.
It's interesting to kind of see the latency between academic discovery and commercial development. And so, for instance, Hopfield networks were discovered 50 or so years ago, but the Turing Award and the Nobel Prize in Physics weren't awarded for them until, just a few years ago. And so a lot of that is not functionality or whether something can exist. Part of it is just the economics of scale, which quantum computing is just blowing away. And on that note, sort of how do you see it branching out further into the hardware space? And because there's a little bit of a dichotomy between something less visible, such as data processing through quantum processors versus an actual in an output being rendered, such as a visual production on film or maybe some sort of a hologram. And so, how do you see that gradually evolving over time, since much of this is based on the physics of waves and what human beings actually experience at a fundamental level in entertainment is light and sound being rendered and then experienced?
So that's a very interesting question, and I think the answer is cool and a little bit surprising. There are not that many applications that have foolproof that quantum computers will bring tremendous impact in, but each of them opens up a world of opportunities. So, for example, we just announced recently work that we did on solving the wave equation using quantum computers. And we've shown that we can, in principle, surpass the strongest high performance computers in problems that they cannot solve, and we can solve at the level of 100 logical qubits or so. Okay, so it's getting to be closer, because the level of 100 qubits will be there in 1-2 years' time. So the idea there was to take a vast area where you have, let's say, a few cell towers radiating electromagnetic waves, and we wanted to analyze what would be the profile of this wave propagation in realistic scenarios where we have reflections from topography or buildings, and you may have other signals interfering with you, and so on and so forth. So this is an application in communication technologies, right? But then mapping out that problem into visualizations in art, for example, it's the same type of equations that look at how wave-like entities propagate, okay? So if you would like to simulate waves in the ocean in computer animation in a very detailed way with extreme precision, much better than what you have today, this is the same type of problem, and you can map out one application and use the same approach in another similar application. So in a similar way, we can do a lot of mapping between different problems and take, for example, problems from, fraud detection in financials and map that problem into, let's do precise image processing and classification in images and so on. So that's pretty cool that you can migrate these ideas from one field to another.
Science aside, raising that amount within a period of about 4.5 years is a massive change. And so I wonder if you would be able to touch on the stages from inception to where we're at now post Series A, because that involves a massive change in employee base and everything from financial reporting to the actual infrastructure you need to operate and corporate governance as well.
There's a long way to go, and there's much more money to raise. So Quantum Art was spun out of the Weizmann Institute from the group of our co-founder and chief science officer, Professor Roy Averi, in 2022. All of the three co-founders, we go back many, many years in academia, industry, and government. And so it was natural for us to join forces and set up this company. And the starting point was that Roy at Weizmann has built the first full stack quantum computer in Israel in any qubit technology with state-of-the-art performance of a few qubits, a small quantum computer. And we understood at that point that this is the right time to go ahead and take it beyond what academia can do in the commercial sense. Okay, so we joined forces in 2022. We raised our seed round, which was $24 million. by 4 Israeli venture capital firms, and we got started. And very recently, we have closed our Series A round, as you said at the opening statement, at $140 million approximately, which is the largest ever Series A round in quantum. Why do we need that? We need that because this is damn hard tech. Okay, we're using very vast multidisciplinary systems that have to do with quantum physics and lasers and electromagnetics and optics and vacuum and software. And all of this needs to play together. And it's a very hard effort in order to bring this at the utmost performance. Amit said that we're working with atoms and they're perfect qubits, okay, or atoms in our case. We just need not to interfere with them. So not to interfere with them and to bring out the most of them is a very, very challenging engineering and even scientific in some senses.
In terms of the architecture, it's reconfigurable. We called it, it's similar to what we would say about it. Like with your FPGA, you can use software to reconfigure your hardware. We called it like a quantum FPGA, at which we can reconfigure the cores and connect them in a quantum way, meaning that we can get to very powerful results while using a very tiny and small system.
Really is incredible at a computational sense. It's a brief last question. Would you be able to touch on how studying with a Nobel laureate provided some of the foundation for developing this years down the line?
I had the privilege to work with Dave Wineland at NIST Boulder 25 years ago. I think Dave is one of the nicest persons I ever met and one of the cleverest ones that I've met. So he's great. And I think a lot of the companies that span out of this hub actually initiated companies like people are coming from many companies that you know of, like Continuum and IonQ, actually were in some of the startups at Europe actually were, these are Dave Wineland students. And it was a very nice and impressive part of my academic life, like learning to work with such a talented guy. And he's very modest and he knows a lot. And so, and when we came there, he already wrote a paper. It was like 200 pages. We called it the book, the Bible. Each one of us took another approach. We took some different approach from the usual approach taken there on using quantum CCD, and we're using other ideas that were actually built later on based on optics and tweezers to take the next steps.
Quantum is no longer a science fiction thing of the far future. It's already here. It's approaching real usefulness in the next 1-2 years, right? It's within sight. On the other hand, this is not like taking a few CPUs and GPUs and putting them together to build a machine. This is a whole different philosophy. It's a paradigm shift. And in order to be prepared for that and not miss the train, people need to start understanding what this could bring as benefit for them today. And today, most of the Fortune 500 companies are already testing the temperature of these waters and trying to do application development and understand what will be the added value and when this will come to them. And so my recommendation for people out there is understand what this is, what it can bring to humanity, how it will change people's lives on the planet. And if you are in a technological organization, just go ahead and get your hands dirty.
Thank you so much for doing this. This was really, really fascinating.
Thanks for having us.
Thanks a lot.